One of the things that Einstein was known for, he actually got a Nobel Prize for it, was something called the photoelectric effect. And what he explored was what happens to metal when you shine a light on it. And the definition of photoelectric effect is when light hits a metal, electrons are knocked off the surface, and that allows an electric current to be generated. And it turns out what we call those electrons that are knocked out of the metal is we call them photoelectrons. Classical physics couldn't explain this, so we have to look now to our new area of quantum mechanics to take a look at this. So if we take a look at this diagram, what's going on is we have light rays coming in. This light ray has a wavelength of 700 nanometers, and it possesses a certain amount of energy, 1.77 electron volts. And the result of this is I get no electrons being knocked off the metal. I take something with a shorter wavelength, which means a higher amount of energy, and I get some electrons coming off. That's what this is showing right here. And these electrons are ejected, and they have a particular amount of energy. V is a velocity, and so they have a velocity of 2.96 times 10 to the 5th meters per second. So they're moving relatively quickly right along. I have an even shorter wavelength of light with an even higher amount of energy hitting the metal, and I get electrons coming off at an even larger velocity. So I see that the energy of the photon is equal to Planck's constant times the frequency. This is actually Greek symbol for frequency. This is a Greek letter nu. We use an F just because V's and N's look an awful lot alike when you're looking at some type fonts. So if this metal is potassium, what is indicated is that we need at least 2 electron volts to knock an electron off the surface. Here in the red case, we only had 1.77 electron volts, not enough energy to knock it off. So if we compare classical predictions, classical physics, Newtonian mechanics predictions, with experimental evidence, we're going to look and see what determines whether an electron is ejected from a metal. Classical predicted that for light intensity, greater the intensity, the more electrons are knocked off. That's what was predicted. What was found was that it was light frequency. So the intensity doesn't affect the amount of electrons. It turns out the frequency does. Kinetic energy of the electrons being knocked off, again, light intensity was predicted. And it was predicted again that the more intense, the more kinetic energy. Again, what was found was that light frequency, and that determines the amount of kinetic energy. So classical mechanics was no help at all in predicting what's going to go on with electrons being ejected from metal or having anything to do in terms of explaining photoelectric effect. What was found was if I had very high intensity, even if it was really, really high, if the frequency isn't high enough, I'm not going to be able to eject any electrons. And this minimum frequency is called the threshold frequency. Threshold frequency generally is F sub T, and the threshold frequency is different for each metal. Okay, Einstein determined that the electron has to absorb enough energy to have overcome the attractive forces of the nucleus holding it to the metal. And the amount of energy it has to overcome is called the work function. And the work function is an equation, and it is Planck's constant times the threshold frequency, and the symbol for the work function is phi. He also found that the amount of kinetic energy emitted by an electron is the maximum kinetic energy, and the equation that you use to find that is the frequency times Planck's constant minus the work function, or the Planck's constant times the threshold frequency. When the frequency is equal to the threshold frequency, I'm just barely knocking the electrons off, and the maximum kinetic energy is 0. The electrons are getting knocked off, but they don't really have any energy to go anywhere. If you want them to move, you need to use a frequency higher than that threshold frequency. So looking at a graphical relationship, here we have maximum kinetic energy on the vertical axis. We have frequency on the horizontal axis. What we have is This is F0. I realize it's hard to see. Here's an F. And the slope is Planck's constant, because if we write out the equation, we've got maximum kinetic energy equals Planck's constant times the frequency plus some y-intercept. Actually, it's going to be negative because here's 0. So rather than plus phi, that's where we get the minus phi, or the minus the work function. So our kinetic energy maximum equation is just a linear equation for the slope of the line. Stopping voltage is something that can be experimentally determined, and what it is the amount of voltage, or the electrical potential, that stops the current created by the flow of electrons. Why is this useful to know? Well, when I use electric eyes or electric beams to start and stop circuits, then it's useful to know what voltage is needed to stop the current flow. Elevators, photoelectric doors are primary ones that are involved in running a circuit, stopping a circuit, causing something to happen by directing a flow of electrons. And if I know what the stopping voltage is, then I know how much voltage I have to apply to cause that electron flow to stop and either close my circuit or allow a different one to open. So for photoelectrons, it turns out that the maximum kinetic energy is equal to Q, which is charge, times the stopping voltage. Let's take a look at an example of this. So I have sodium metal, and I hit it with a light of 1 × 10⁵ hertz. So there's my frequency. Work function, or phi, for sodium is 2.28 electron volts. And I want to know what is the maximum kinetic energy of the electrons leaving the surface. So go back to my equations, and I know that the kinetic energy maximum is equal to Planck's constant times the frequency I apply minus Planck's constant times threshold frequency. But remember that Planck's constant times threshold frequency is my work function, phi. So I'm going to take Planck's constant, which is 6.63 times 10⁻34 joules seconds, times frequency, 1.0 times 10⁵, and I want to get that into electron volts because this is going to be joules. So I'm going to divide that by 1.6 times 10⁻19 joules per electron volt. So there's my HF. And now I'm going to subtract the work function. Well, they tell me the work function is 2.28 electron volts, which is why I had to get this equation into electron volts. So this bit right here is 4.14 electron volts minus 2.28 electron volt. And so my maximum kinetic energy for these electrons being ejected is 1.86 electron volts.